Hello everyone, Lab 4 is about discrete Fourier transform. In short term it's called as DFT. DFT is one of the most important transform in digital system and in signal system in general. It is basically converting a sampled function from its time domain to the frequency domain. DFT is normally calculated using computers and using FFT algorithm, but it's possible to use the DSP boards to calculate DFT coefficients. In a mathematical form, if we have a discrete function, discrete signal x of n, which is x0, x1, x2, and all the way to xn minus 1. So it means that x of n has basically n samples. To calculate the DFT coefficient, we can use the general formula. It says x of k is equal sigma n from 0 to nx minus 1 x n exponential of minus j 2 pi k over nx times n. Nx is the number of DFT points, which is normally a power of 2. Let's consider nx for our experiment to be 4 for simplicity. The formula is going to be x of k is sigma n from 0 to 3 x of n e to the minus j 2 pi k divided by 4 n. So if I expand this formula, then it would say x of k is equal x0. So first I'm putting n is equal 0. I'm subbing n equals 0 into the formula, in the sigma. It would be x0, x to the power 0, which is 1. So x0 is going to be alone here, plus x1 e to the power minus j 2 pi over 4, 2 pi k over 4. N is equal 1. So I don't have to put anything here, plus x2 e to the power minus j 2 pi k 4 times 2, and finally plus x3 e to the minus j 2 pi k 4 times 3. So if you look at this formula, you can see that first we need to create the x0, x1, x2, and x3. And we know that in Simulink, if you have your, let's say, ADC block, and the samples are keep coming here, so if you use multiple Z inverse blocks, which is the delay blocks, it's gonna give me the different, let's have another block, let's say here. So the first, if let's say x0 is here, x1, x2, and x3, so these are coming to the ADC block. Each time that a transfer is happening, this x1, x0, x2, x3 are going to go to the different blocks. So at the end, after 4 transfer, x0 is going to be here, x1 is going to be here, x2 is going to be here, and x3 is going to be here. So in order to create this, we can just simply use the Z inverse blocks. And then we need to create K's. So for K is going to be from 1 to 3. So K is going to be from 0, 1, 2, 3. So in this formula, I'm going to just use this case. So it's going to be from 0, 1 to 3. So we need to use a counter. So a counter is going to be used to create the count. So this is going to be created by a counter. To give you an example, I'm going to calculate the coefficient for 1. So x1, I have to use this formula and just sub k equal 1 in the formula. So this gives me x0 plus x1 e to the minus j 2 pi over 4 plus x2 e to the minus j 2 pi 4 times 2 plus x3 e to the minus j 2 pi 4 times 3. So as you can see here, there are coefficients at this point: 2 pi over 4, 4 pi over 4, and 6 pi over 4. These are basically only constant blocks. So if we define some constant blocks equivalent to these formulas, and then we have to calculate e to the minus j for that constant block. There is a block which is called exponential exponential block, which I'm going to show you in next few minutes. Is going to be used to calculate this part, and then you need just a multiplier to multiply different instances that you have here, here, and here, multiplied by to the exponential block, and then you need an adder to do the additions. So in this case, all coefficients of DFT could be calculated, and then you can simply implement it on a DSP board. So this is part of the Simulink model that you need to use in the lab to calculate the DFT coefficient. The incomplete parts have to be filled out and completed by yourself. So you can see that we have the Z inverse models to create delay. Don't forget that if the samples are coming from A to C, then after a few transitions, this is always going to give you x0, x1, x2, and you have x3 here. So we are using a 4-point DFT. That's why we have x0 to x3. And then we have a counter here to create the k values. You remember we already explained about it. K is going from 0 to 3, and make sure that you are using this type of counter limited, because Simulink has different type of counters, but we are going to use the counter limited and set it to give us the 0, 1, 2, 3. You may need a delay here, depends on how you implement your model, or you may not need it. For my model, I had to use a delay here to make sure the values are correct. Here we have this counter multiplied by minus 2 pi over 4, because if you look at the formula for this part, for x1 is going to be minus 2 pi over 4. So let's say if the k is equal 1, so when the counter is counting 1, at count 1, then this here is going to be minus 2 pi over 4, and this is going to be exponential, complex exponential. So this block is available in Simulink. So the output is going to be minus j 2 pi over 4 here, and this is x1. So this is going to be x1 e to the minus j 2 pi 4, which was one of the terms that we needed to calculate the DFT coefficients. So this is coming here, and this is basically x0. So in this model I have already calculated two terms. This is one term, this is another term, and this term has to be completed by you. And then next step is to calculate the inverse DFT coefficients. To calculate the inverse DFT, we can use this formula. Basically, x of n is going to be 1 over n sigma k from 0 to n minus 1 xk e to the j 2 pi k over n and this n. So if you look at the formula and compare it to the formula for DFT, the only difference is that in the other formula you had e to the, so this was e to the minus j 2 pi k n times n. So basically the model is the same model, so it's exactly the same model. The only difference is that the constant block is going to be the different for DFT and IDFT. So for DFT, the constant block are going to be the 2 pi over n minus 2 pi over n. For IDFT, the constant block are going to be 2 pi over n. And of course there is like this n and this n here for different n's. So it means that it's a matter of changing only a sign. A negative sign is going to be this. So when you create the DFT block, so consider that this is your DFT model. You just copy paste this DFT model. So you create the next model, which is the copy of DFT. So copy of DFT, and then you change the sign. Change the signs. And that would be your IDFT model. Then what you need to do, if to check to see if your model is working for DFT and IDFT, you need to implement this whole model. This is your ADC going to the DFT model, and then the DFT model is going to IDFT model. The output of the DFT model is going to the input of DFT model, and the output of IDFT is going to your DAC. So if you have ADC and DSC connected in this way, it means that if you use a function generator here to give you a sinusoidal signal, and you connect this to scope, to oscilloscope of course, you should be able to see the same sinusoidal signal. In this way you can find out that okay, your DFT model was working and your inverse model was working, and when you put the model and inverse together, it gave you the original signal here at the output. So this is the way that we check and test the DFT models and inverse DFT models. I hope this tutorial was able to give you enough hints to develop your model. Just make sure that the samplings are correct, The samplings should be 1/8000 for the counter and for the most of the module, because you are using 8000 Hertz sampling frequency. Make sure your DAC is also 8000 sampling frequency, and that should be about it. Good luck.